So let's continue on this, and we're gonna work on our plane. And the first thing is, let me remove this. And the first thing I want is to create the two vectors that we talked about. So we need a vector that goes from here to here and from here to here. And we're gonna do that using vex because it's much easier. So the first thing, we need to import the position of point 15. So vector, I'm going to call this pos 0 for position 0, and that's going to be the point number 15. And then we're going to use an expression called neighbor, and let me this function, we're going to give it the geometry, of course, and an input number, the point number, which we want to retrieve the neighboring points to it, and then an integer. And the neighbors are going to be, for this point, are going to be 11 and 14. And 0 will give us back point number 11, and 1 will give us back number 14. So it's basically an array that we need to provide which neighbor we're interested in, and we just want the first and second. So, and that's going to return the point number. Okay, it's not going to return the position, it's going to return a number for us. So let's do this. Let's do neighbor 1. Okay, and we want the neighbor of the first input, the geometry, and then the point number is 15. That's our guy there. And then we want the first neighbor. So let's take a look, and that's number 15. Number 11. See, neighbor 1 is number 11. So let's do the second neighbor, neighbor 2, and that's number 1, and that's number 14. Cool. So we don't want these guys. We don't want to store their ID. Just put them so we can view them. So it's an integer, and then we want to import the position of these points. Now we have their ID. So position 1 for neighbor 1 is going to be this guy, and then the point ID for neighbor 1, and then position 2 is neighbor 2. So we have position of this guy, and this guy, and we want to compute vectors now. So we want this guy and this vector, and I'm going to call them vector A. I'm going to call this A and B, and that's going to be pos 1 minus pos 0, and same thing for, actually let's store this V at A, and then pos 2 from pos 0, and this is B, and I want to make sure that we normalize this. We don't need any length, we just need the orientation of the vector, and it's best, or we have to normalize it to make sure that the cross product that we're going to compute is valid. So let's view this quickly. I'm going to store A as n, and I'm going to multiply it by 1000 so it's visible. I'm going to store B in velocity so we can see it in the viewport, and that's our A axis stored in n, and this is our velocity, and this is our velocity showing B axis, so you can see both of them. And then we're going to compute the cross product. So let's overwrite n again, and this time I'm going to compute the cross product between A and B, and that's going to give us the up vector, or an orthogonal vector to that plane. So cross between V at A and V at B. Okay. And now we should see it's multiplied by 1000 so it's visible, and that's our up vector. Cool. So let's call this up, And now we have 3 vectors. And I only need 2. And we, for the quaternion, we only need 2. I'm going to use a point VOP because it's easier to do all this stuff in with nodes. But this block here would take a lot of nodes inside the point VOP, so that's why I did it here. It's much easier. So we have up. I don't need this guy. We have A, B, and up. So let's import all of those. And it's a vector. Let's import A, B, and up. And for now, I'm going to transform this geometry back using a transform node, and then we'll do it in SOPs. I'll explain how to do it in SOPs. So we're zeroing out everything, basically just approximating that. And what we want now with the point VOP is to remove the orientation from this. Okay. So we have our 3 vector. We're going to use a node called look at, and this is going to generate a rotation matrix, a 3x3 matrix, or a quaternion, and it's a 3x3 matrix, and it's going to store the rotation. And what we need is an up vector, which is our up, and then the 2 is going to be B in this case, which is this guy. And the from, I'm going to set this to 0, 0, 0. And we need to convert this matrix 3x3 to 4x4, so we can combine it with other things that we'll talk about in a second. So we convert it into a 4x4 matrix, and then we're going to multiply the position P by this matrix. And let's take a look. Okay, let me remove this guy. Okay, so let's do one more thing. Let's apply the transformation as well, and because I think we need both of them for this to work properly. So I'm going to create a translate node, and this is going to create a transform matrix. Okay, it's a translate matrix, and what we need is the amount that we need to transform with. Okay, so let's import point number 15. So import point attribute, and let me make sure. Okay, so point number 15, we're going to get the vector, which is the position of point 15, and that's going to be our translate amount. So this is the first input, and a constant. And that's our translate information, and then we're going to multiply the 2 matrices. We're going to concatenate them. Okay, so first we need the rotation, and second we need the translate. And it's very important to do to concatenate matrices in the proper order, because the first one is scale, and then rotation, and then transform. If we go up to the geometry, you can see here, transform order, this is how the matrices are applied. Okay, it's a scale, rotation, and translate. We can change this, but it's going to give us completely different result. And the standard is SRT, so scale, transform, and rotate. Okay, so back here, I'm going to multiply all this, the transform and rotation matrices, with the points. And one thing, a very important thing I forgot to do is to invert this, because right now we're applying the same transformation again. So we're going to invert all of this, and boom, our geometry is back at 0, 0, and it has proper orientation. And that the orientation actually works if I did this here and just apply the invert. It's going to work. I forgot to apply the transformation, to invert the transformation, sorry. So that's pretty much it. We need 2 vectors. Let's go back. So we need two vectors. We need to find a z-axis and an x-axis, and then from there we're going to generate an orthogonal up vector using the cross product, and then we're going to take two vectors and feed those into the quaternion and use that to generate a rotation matrix using the lookat node, and then we're going to apply the inverse of that rotation and the inverse of the transformation. And the transformation matrix is just the distance from this point to the center, and we're going to apply all that to each point. And that's pretty much it. So let me turn this off. Okay, so the main reason I used this and I did this in Vex because it's much easier and simpler to do subtraction and comparison and things like that in Vex, and then I find it easier to do things like the lookat and matrices inside of VOPs, because it can be really tricky if we decided to do all this in Vex. Now let's take this and so I'm going to create a for each loop, and what I want to do is I want to create a bound geometry around all these guys. Okay, so now we're encapsulating that geometry in this, and I'm going to tick on oriented bounded box, which will fit an oriented bounded box. And let's take a look at the geometry. And now we have wrapped everything in with boxes, basically. Now what I want to do is, let's go back. I want to pick a point, or let's do it on one of these guys. Okay. So not that. So let's pick this. And let's do it here. I'm gonna copy these two nodes, and I wanna transform this back to the origin. So what we need to do is we need 2 points. Okay. And let's do it on this geometry. So we're going to take, for example, point number 7 or point number 6. And let's create it here. Int point ID is equal 15 as 6 at this time. And I'm gonna replace these guys. Okay. And now we have this geometry aligned along this axis. Okay. It's fine. We can keep it aligned to this axis and just apply transform like that. So it's facing the up axis, or we can just scale do the Voronoi along this axis, which is perfectly fine. Now I don't want to use the original geometry. I want to apply a bound and use oriented bounding box, and for this bound I'm going to use point number 1. Okay, so yeah, let's do point number 1, and now we have this oriented. Okay, let's try this same block here onto that for each loop that we did. So we're running over each geometry and we're computing the bound, and I want to transform them back to the origin and remove the orientation. Cool, so we did that, and look, we have some that are facing this axis, some are facing this axis, and some are facing this axis. And this is not ideal because we cannot apply the Voronoi like this. So what we need to do, the reason for that is because the pieces, some of them are facing this way, some of them are facing this way, and this bound, that point number 1, the point number 1 that worked in this example didn't work on another example. And what we need to do is we need to figure out a way for the system that will find what is the longest vector along this geometry. That is going to be our y-axis. Okay, so let's say we have point 1 in this example, and we have two vectors. Okay, we're going to have this vector from 0 to 1, and then vector from 2 to 1. One of them is very long and the other one is very short. We want to use the longest one to be our y-axis, to be our up axis. So we're going to compute the length of these two vectors, and then the longest one is going to be our y-axis. And if we apply this to all our geometry, we are going to always, let's go through some of them. So in this example, we have point number 1, okay? This is going to be our longest axis. Okay? If we, let's do this single pass. And now we're on a different piece. And disable this. Reset cache. Okay, so now where is point number 1? Still, this is going to work. So let's keep going. So okay, point number 1. This axis is going to be the longest. In other cases, the first neighbor is not going to be the longest one. It's going to be the shortest one. Okay, and in that case, we have to use the longest one from this result, and we're gonna do that in the next video, and this will help with the alignment of all the geometry. So if we figure out what is the longest axis, we can tell it, okay, this is what you need to be pointing at, and use that. And this way we're going to align everything to point to the same direction. We can apply our wood fracturing and then apply the inverse transformation back. Oh, actually one more thing I wanted to do. So we have let's do it now. So we made bound geometry, okay, and we transformed this guy back. Now I don't want to transform this bound geometry. I don't want this. And what I'm going to do is I'm gonna bind export this transform matrix that we made. I'm gonna call this transform matrix. Very simple, and it's a 16 float. It's 4x4, and I'm going to use a wrangle node. I'm going to take the first input, which is our original geometry, and I'm going to read that matrix. We're going to read that matrix from point number 1. So we need we're going to create a matrix. I'm going to call it full transform. And we're going to import this information from the first input, which is this guy here. And the attribute is called, what did we call it? It's called transform matrix. And the point number 0, it doesn't matter because all the point has the same attribute. And then we're going to apply that onto the geometry. So we're going to multiply the position by that matrix. And I'm calling it full transform. Let's see. Yeah, this should work. And let's take a look. Okay. Yeah, it should work just fine. So we have the geo here. I'm not sure why it's... Maybe you guys are seeing something that I'm not. Try point number 1. I'm gonna copy this. Sometimes the node just gets crazy like that. The syntax is correct. So v at p interesting. Okay, so this definitely should work. I'm not sure what's happening here. Oh, I see. Deformation wrangle. No idea when this got created. I need a point wrangle. Okay, so we're transforming this back to the origin, and then we're applying this transformation to the actual geometry. So if we take a look now, this is the actual geometry for the entire structure, and then once we align all of it along the same axis, we're going to be able to do the Voronoi fracture and then apply back the transformation. So we'll continue that in the next video. Thank you guys for watching, and see you in a bit.